Okay, welcome to this lesson on angle proofs. We are going to be in the first part, which is going to be the first video on angle proofs. We're just going to go over some common reasons that are used in angle proofs. And then I'm going to make a second video where we actually do some angle proofs. For some reason, this keeps scrolling down when I do not want it to. So we'll cover the first half of the notes in the first video, and then the actual angle proof examples in the second one. All right, so let's jump right into this. When you write a proof, you will need to justify your statements, of course, with definitions, theorems, postulates, and properties that we have learned. So we're going to start by reviewing some definitions for angles that may be used in some proofs, and I will highlight ones that we use very frequently. So two congruent angles, by the way, this whole first page is basically a review of things we've already learned. So the second page is going to contain more new information. So I'd say over half of this should be review as far as the rules are concerned, because we learned them in the first unit. So the definition of congruent angles are angles with the same measure. So maybe if you have a statement in your work somewhere that the measure of angle ABC is congruent to the measure of angle XYZ, you can use that to conclude that angle ABC is congruent to angle XYZ. Okay, this goes both ways because all good definitions are biconditional. So you can, if you're given the measures, you can say the angles are congruent. If you're given that the angles are congruent, you can say that their measures are equal. And I should have just an equal sign between the measures because we're referring to numbers. So you can use it to move back and forth between equality and congruence. All right, definition of an angle bisector. If a ray bisects an angle, it divides it into two congruent angles. So let's say I say ray BD bisects angle ABC. So you can use that to conclude that two angles are congruent. That would mean that angle ABD is congruent to angle DBC. Now you could draw a picture for that if that helps to understand that. So ray BD is bisecting angle ABC. So we can conclude that the two angles are congruent. The reverse is true. If you have that the angles are congruent, you can conclude that BD has to be an angle bisector. Again, definitions, biconditional. Definition of complementary angles, two angles which have a sum of 90. So if I say angle 1 complements angle 2, you can use that to conclude that measure angle 1 plus measure angle 2 is equal to 90. You can also go backwards with that. Supplementary angles work the same way. If I say angle 1 supplements angle 2, you can use that to conclude that their measures add up to 180 and the reverse. Okay, definition of linear pair. When we're doing the definition of linear pair, we just use that to look at a picture and say, hey, these are linear pair angles, because you can see in the picture you have two adjacent angles whose non-common sides form opposite rays. So if I look at this picture, I can conclude in my proof that angle 1 and angle 2 form a linear pair, or are a linear pair. A lot of times we abbreviate that. So if you were to see this in a proof, you would say it was because of definition of a linear pair. Now, if we conclude they add up to 180, that's going to be something different. That's the linear pair theorem. So we have a linear pair definition and a linear pair theorem. I always like to say in class, the definition tells you what it is. It is a linear pair. It is a perpendicular pair. It is a set of vertical angles. The theorem tells you what it does. If they're a linear pair, we can say they're supplementary, or we can say they're complementary, or we can say they're congruent based on what the type of angles are. So if we see a picture here like this, okay, we have two adjacent angles, 1 and 2, whose non-common sides form a right angle, then we can conclude that they are a perpendicular pair. Angle 1 and angle 2 are a perpendicular pair. All my pens are dying. Good. Okay, so you can conclude that. Of course, all of these you can go the other way. Then again, vertical angles, non-adjacent angles formed by intersecting lines. We can conclude angle 1 and angle 2 are vertical. If you see angle 1 and angle 2 are vertical in the proof and you see this picture, then afterwards you're going to write definition of vertical angles. We're calling them vertical because that's what they are. We don't say they're congruent with definition of vertical angles. No, we say they're congruent with the vertical angles theorem, which is going to be on the next page where all the theorems are. All right, angle addition postulate. So let's say you've got a picture like this, okay? You have point D interior to angle A, B, C. So we learned interior and exterior of angles. Then we can conclude in our proof as a statement, measure angle ABD plus measure angle DBC equals measure angle ABC. And then the reason you would write for that would be angle addition postulate, because you add up the parts to get the whole. Reflexive property of congruence, every angle is congruent to itself. So if you see in there anywhere in a proof an angle is congruent to the same exact angle, that will be definitely reflexive. We won't use that a lot right now. We will use it later when we do triangle pictures. It's okay. Oh, no, that's not right. Sorry. Like we'll have a picture like this, and we have two overlapping triangles. We'll say angle A, which is right here, in this triangle is the same as angle A in the other triangle because they overlap. But we won't be doing that a lot in this unit. Symmetric property of congruent angles. If angle A is congruent to angle B, then angle B is congruent to angle A. We only use that in a proof when we need to flip something around to make it match the proof. Transitive property of congruent angles. We will use that a lot. So I'm going to go back and highlight that. I'm going to have to go back and highlight a few of these. All right. If two angles are congruent to the same angle, then the two angles are congruent. So yeah, both of them are congruent to angle B, so that means angle A must be congruent to angle C. We'll use that a lot. Other rules from this page that we will use a lot, definition of congruent angles. Yes, we'll use angle bisector, complements, supplements. A lot of times in proofs, a lot of times we will skip over these three. So this one, and this one are often skipped over. However, if I put it in a fill-in-the-blank proof, you need to be able to fill it in. This one we will use a lot, angle addition postulate. And those are the most frequently used ones on this page, okay? So we have 6 frequently used ones. Okay, the next page is where all of our theorems are, including our special right angle theorems at the bottom. Okay, angle subtraction theorem. That is just like one step above the angle addition postulate. We won't use it a whole lot, but at times you'll find that it's a time saver if you think to use it. If you don't think to use it, your proof's just going to be a tad longer. So I'm not going to highlight that one, but we are going to prove this one. So it says if D is in the interior of angle ABC, it's very much like the segment subtraction theorem that we did before. Okay, then we can conclude that the measure of angle ABD minus the measure of angle ABC. So in other words, we can take AB, oh, that should be ABC. Oh, the measure of angle ABD equals, I'm sorry, I didn't write equal sign. So the measure of this part of the angle here is equal to the entire angle minus the other part. So yes, if you subtract one part from a whole, you get the other part. Okay. So if you see a statement like that, you would just describe it with angle subtraction theorem. Bisected angle theorem is another one that is true and everything, but we don't use it a whole lot. This one really compares and contrasts with the definition of bisected angle or an angle bisector. The angle bisector definition allows you to conclude that the two angles are congruent. The bisected angle theorem allows you to conclude that each part is half of the whole. It's very similar to the midpoint theorem versus the midpoint definition. So each part is half of the whole on the bisected angle theorem. That should be array BD. So basically the same picture applies to both this rule and that one. We won't use that one a whole lot. This one we will use a bunch, and this one we will use a bunch. They're like, I guess you could say they're sister theorems having to do with complementary angles. We do use some, but we don't use quite as much. And vertical angles, we're going to use those all the time. All right, perpendicular pair theorem. If the non-common sides of two adjacent angles are perpendicular, all right, so here we go. 1, 2, okay. Then the angles are complementary. So this implies angle 1 complements angle 2. Okay, that really smacks of being similar to the complementary angles definition. Okay, if I tell you the angles are complementary, then you can conclude they add up to 90. If you see this, you don't go straight to 90. First, you say they're complementary. Then you use the definition of complementary afterwards to say they add up to 90. So those often work in conjunction. The linear pair theorem says if you have a set of linear pair angles, then you can conclude that they are supplementary. Okay, that's similar to the definition of supplementary angles, which you could use after this to say they add up to 180, okay, which is up here on the previous page. Oh no, where are they? Right here. All right, after you've shown they're supplementary, then you can say they add up to 180. All right, now let's talk about the congruent complements theorem and the congruent supplements theorem, which are different because it's not just about having two angles be complementary or supplementary. You're actually going to have a third angle in this. I'll do congruent complements first. If two angles that complement the same angle are congruent, so any two angles that complement the same angle are congruent. So let's say I have a picture like here, angle 1, and it is complemented by angle 2, okay, and they make a right angle. But then I also say angle 1 is complemented by angle 3, so we have another right angle here. So if I were to say angle 2 complements angle 1, and then I also say angle 3 complements angle 1, we can conclude based on that since these two different angles complement the same angle, that means those two different angles are congruent. Now, if I put some numbers on this, that'll make it make so much sense, so much more fast. So I'm going to do that now. Okay. So let's say this angle is 60 degrees. All right, if angle 2 complements it, that means it makes it add up to 90. So angle 2 would have to be 30 degrees. All right, angle 1 is still 60 degrees. If angle 3 complements it, it would have to be 30 degrees. So since this angle and this angle both make this add up to 90, they both have to be equal to do that. Okay. We will use that sum, and we will use its like little twin theorem, the congruent supplements theorem, even more. So let's say we have a situation like, I'll draw a parallelogram for this one. I'm going to say angle 3, angle 4, and angle 7. So I'm going to say we're given that angle 3 supplements angle 7, and we're given that angle 3 supplements angle 4, because if it's a parallelogram, opposite sides are parallel. So they're same side interior angles. These two, oops, it got very small. We don't want it that small. These two angles over here are same side interior angles for these parallel lines. And these two angles are same side interior for these parallel lines. So they are supplementary. So that would allow us to conclude, since 7 and 4 both make angle 3 add up to 180, that means angle 7 has to be congruent to angle 4. So the congruent supplements and congruent complements ends with some angles being congruent. That's why they're called congruent theorems. And again, you could feel free to throw some numbers on here to make this make sense. Let's say this angle is 145. Okay, well, for angle 3 to supplement angle 7, it would have to be 35 to add up to 180. And then for angle 3 to supplement angle 4, this would have to be 35. So you can see these two have to be congruent, just as these two have to be congruent. All right, we'll use that theorem a whole lot throughout the course of the year. All right, vertical angles theorem says vertical angles are congruent. So 1, 2. First, I would say angle 1 is congruent to angle 2. Oh, no. First, you would say angle 1 and angle 2 are vertical angles. Okay, a lot of times we skip over that. Angle 1 and angle 2 are vertical. Now, that would be justified by the definition of vertical angles, because you're calling them vertical. You're seeing the picture and you're concluding that they're vertical. Okay, so remember the definition says what it is. It is vertical angles. The theorem says what it does, and what it does is that the angles are congruent. So that's the difference between the vertical angles theorem and the vertical angles definition. All right, just a couple more. Let's talk about our special right angle theorems, okay? These theorems don't have names, so we're just going to abbreviate like crazy to get them into our proof boxes when we have to. All right angles are congruent. So yes, if I say angle 1 is a right angle, abbreviating with RT angle, angle 2 is a right angle, we can conclude that angle 1 is congruent to angle 2. And that's a very short, nice proof to do. It's a nice proof to put on a test for that reason. The next rule would be theorem, perpendicular lines form congruent adjacent angles. Okay, so perpendicular lines, 1 and 2, they form two angles that are next to each other, and they are congruent. Of course they are, because they're 90. So that would allow us, if I say I have some perpendicular lines, I can say angle 1 and angle 2 are congruent. So I'll just put a congruent symbol between them, because they both have to be right angles. And then we know that all right angles are congruent from the rule we just covered above. All right, next, if two angles are congruent and supplementary. So you have two angles supplementary, like they're making a linear pair, and they are congruent. This angle is congruent to this one. Then it has to be true that angle 1 and angle 2 are right angles. That is true as well, and you can use that when you need to. If two congruent angles form a linear pair, then they are right angles. Okay, so here, these angles are congruent and supplementary. Oh, Okay, so maybe this one I'll make a little different. Let's say angle 1's congruent to angle 2, because it doesn't say they're in a linear pair here. It says it in the next one. So congruent to angle 2, angle 1 supplements angle 2. Okay, then you would say they're right angles. So that would be fine. All right, two congruent angles form a linear pair. So this one, we have a linear pair, and we have two angles that are marked congruent. They aren't necessarily marked right angles. They're marked congruent. But because they have to add up to 90, and we're dividing it equally between them, we know, they add up to 180, and we have to divide the degrees equally between them. They both have to be 90. So angle 1 and angle 2 are right angles. So both of these allow us to conclude some angles are right angles, but with slightly different given information. And then the last one. The definition of perpendicular lines is that they form a right angle. Definition, perpendicular lines that intersect at a right angle. A theorem that would follow from that is not only is they intersecting at one right angle, all of the four angles are right angles. So the theorem says all four angles are right angles. So if I gave you this picture with L and M, and I named the angles 1, 2, 3, and 4, having the fact that L is perpendicular to M would allow you to conclude angle 1, angle 2, angle 3, and angle 4 are right angles. That proof takes a minute to prove. That would be a proof I would only give you as fill in the blank, because every single reason is easy to fill in, but there's a lot of them to work your way around detailed and prove that all of them are right angles. All right, so this is the end of the first part of this lesson, just on going through all the common angle rules that are used in proofs. Okay, I didn't include definitions of perpendicular and parallel lines because those aren't angles. They create angles, but they aren't themselves angles. But they are previous information we have in our little pocket of information. Join us for the next lesson where we'll actually do a few angle proofs using these rules, and make sure to practice all these rules with a Quizlet, matching, multiple choice, learn, whatever, so that you can make a test and practice them and get yourselves really familiar with them, as well as doing the two-step angle proofs where you get to practice using every reason one time.